Okay, so the last thing that we have to cover is power, and this is pretty easy. It's the amount of work done divided by the time taken to do it. That's it. The symbol for power is a capital P and the units are watts. The symbol for watt is a capital W. The equation for power is in the definition. Power equals work over time. That's it. So W is work, and I know it's a little bit confusing that the symbol for watts is the same as the symbol for work. Deal with it. T is time, and P is power. Now, since the units for power are watts and the units for work are joules, the units for time are seconds, 1 watt is just equal to 1 joule per second. So that's where that unit comes from. That's pretty much it when it comes to power, so let's just jump into the two examples. First one, a force of 235 newtons is applied at a 45-degree angle over a distance of 6 meters for 7 seconds. A, find the work done. B, find the power. So what's happening, you've got any object, it's being pulled by a force at that 45-degree angle, 45 degrees, and it's moving. So our given information, we know that just call it a tension force, it doesn't really matter. The tension force is 235 newtons. The angle phi is 45 degrees. The distance is 6 meters, and the time is 7 seconds. Part A is asking us for the work. Part B is asking us for the power. So starting with part A, let's draw the work diagram. You've got the force applied in this direction. The object is moving this direction, and that's 45 degrees. This was a 235 Newton force, and the distance was 6 meters. Work equals FD cosine phi. Work equals 235 newtons times 6 meters times the cosine of 45 degrees. And we get 997.02, keeps on going, joules. 1 sig fig, work is about 1,000 joules. Simple problem. So now part B, we're looking for the power. Power, this is part B, just equals work over time. So we want to use our unrounded work, 997.02, keeps on going joules, divided by our time, 7 seconds. This equals 142.43, keeps on going, watts. 1 sig fig, power is about 100 watts. Pretty easy. Let's just do the next example and then we'll be done. It tells us that Jim has 1,500 watts of power as he climbs the stairs in 4.0 seconds. If the stairs are 2 meters high, what is the contact force equal to as he climbs the stairs? So going on here, we've got stairs. Jim starting at the bottom of the stairs, and then he's going to climb and get to the top of the stairs. So let's list what we know. It tells us that Jim has 1,500 watts of power, that he climbs the stair in 4.0 seconds, and that the stairs are 2 meters high. So the distance that he's going in terms of where he starts to where he ends up is going to be 2 meters. Because we're only looking in terms of gravitational potential energy. If he starts here, this is the base level. This would be the height technically at B. So that height at B is equal to the distance covered by the force causing him to go up the stairs. And when we say contact force, we could also call it a normal force. he's got his weight going down, and then it's a contact force, or if you want to call it a normal force, from the stairs equal to the gravity as he goes up. And I say equal just because you pretty much usually climb stairs at a constant speed. So given all of that, we want to find what that contact force is equal to. So first, given the power and the time, power equals work over time. So power times time equals work. Power, 1500 watts, times the time, 4 seconds, equals work. So 6,000 joules is the work. And again, how those units work out, a watt is a joule per second, times seconds leaves us with joules. Okay, so we know the work. We also know that work equals FD cosine phi. So work over D cosine phi equals the force. How do we know what phi is? Well, work diagram. Contact force is directed up. He's moving up. So my phi is 0 degrees. So work over D cosine phi, so this is 6,000 joules, divided by the distance, 2 meters, times the cosine of 0 degrees equals the force. 6,000 divided by 2, 3,000 newtons equals contact force. I believe this was only 1 sig fig, so we can just leave it like that. So that's how we use power. It's just one added equation to any of these problems. Again, it's not terribly difficult to use. Power is just work divided by time. So this was an example of how we could use power to then find something dealing with work. We could also use it and go further if we wanted to look at energy, but it was just asking for, in this case, a force.